Hi everyone, I'm about to start the solutions for the transformations of functions assignment, so follow along with me. And if you want to just skip to a specific question, you can use the time tags in the description of the video and go directly there. Alright, so let's start. So as you can see, this is the original function. It sort of looks like a very strange sort of W, but I did this intentionally just to show you that there are different points and to show how this entire graph will transform depending on the question, of course. So the first thing you should do, the easiest thing to do, is first list the endpoints of this function. So for example, this point right here is -2, 2. So the coordinate is -2, 2. And list them down because it just makes it easier, as you'll see later on. This point right here is -1, -2, -1, -2. This point right here is 0, 4. The x coordinate is 0 and the y coordinate is 4. This point right here is 1, 2. So that's 1, 2. And finally, oh, sorry, that's not right. This point right here is 2, 1. Sorry, the x is 2 and the y is 1. It's 2, 1. And finally, the last point right here is 3, 3. So it's 3, 3. So you'll see this sort of set of coordinates for all the graphs over here, and I'll show you basically how we can get the different transformations. So let's look at this example. In this example, what I have over here is I had y is equal to 2f of x, and this right here, this sort of set of points, as I sort of mentioned before, this is our original f of x. So this is the original set of points, and the transform function looks like this very stretched w over here. So let's see how we got from here to sort of this set of points. So the first most important thing is to sort of consider what the transformations are. So if you recall, there's an order to the transformations, and I said it was RST. So in other words, the first one was a reflection. Now, as we can see, that there's no negatives here. The negatives sort of in front of the coefficient of f of x, or inside, or in other words, the coefficient of the x in the argument. If one of those are negative, then there's a reflection. But in this case, neither of them are a reflection, so we have no reflections. The second one was S, which stood for transformations. Which stood for stretch. Sorry, it stood for stretch. And as we can see, there is a coefficient of 2 in front of the f of x, which tells us that there is a vertical stretch. So I'm going to write Vs, which stands for vertical stretch, and it's by a factor of 2. So I'm just going to write Vs by 2, just for short. But on the test, I really want you to write vertical stretch by 2. And then finally, the last one is translation, which means basically it moves left or right or up or down. And in this case, we can see that there's no translations. There's no plus or minus or even inside the argument a plus or minus, so therefore there aren't any translations. So the only sort of transformations that we have is the stretch, which is a vertical stretch by 2, which means that all the y coordinates get multiplied by a factor of 2. So if we had to basically show how these set of points, this is the original set, how they would transform, right? So this is 2f of x. So as we said, since the stretch is a vertical stretch by 2, all the y's will be multiplied by 2, but the x's stay put. There's nothing being transformed in the x's. So since the x's stay put, it's -2, -1, 0, 2, 3. Right? They stay put, nothing happens to them. However, all the y's get multiplied by 2. So this becomes 2 times 2, which is 4. -2 times 2, which is -4. This becomes 8. This becomes 2. And this becomes 6. So as you can see over here, now what we have to do is just plot these coordinates. So the first coordinate, so this -2, 2 becomes -2, 4. So -2, 4, which is that point right there. -1, -4, so -1, -4, which is that point right there. 0, 8, which is 0, 8, and that's that point right there. 2, 2, which is 2, 2, which is that point right there. And finally 3, 6, so 3, 6, which is that point right there. And then if you just connect these lines, so maybe I'll just do that with this tool right here. Let's use blue. Right, so if I just connect these lines right here, I get that, then I get that, then I get that, then I get that, and that's basically how I got this graph. So remember, this was the example. Now let's actually move on to some of the transformations that we see over here. All right, so the first thing we should do is, remember, always list what the transformations are. So let's look at R. So this is number 1. So this is number 1. So y is equal to 1.5x. So it's number 1. As we can see, there's no reflection over here. So no reflection. Let's look at S, and then let's look at T. Okay, so for S, we can see once again that there is a stretch by 1.5. So basically, I'm just going to write vertical stretch by 1.5. And for the translations, we don't see any plus or minuses, so therefore there's no translation. So let's see how this set sort of transforms. The x's stay put because we only have a vertical stretch which only affects the y's. It does not affect the x's. So the x's stay put. And but for the y's, all of them get multiplied by a factor of 1.5. So 1.5y. So if we do this, basically this becomes -2, -1, 0, 2, 3. And since all of these get multiplied by 1.5, this becomes 3. 2 times 1.5 is 3. -2 times 1.5 is equal to -3. 4 times 1.5 is 6. 1 times 1.5 is simply 1.5. And finally, 3 times 1.5 is 4.5. So all we have to do now is just plot these set of points. So -2, -2, 3 will be here. Okay, -1, -3 will be here. 0, 6 is 0. This is 4. This becomes 5, 6. Right there. 2, 1.5. So this is 2. 1.5 will be somewhere here, just above. And finally, 3 and 4.5. So 3. This is 3. This is 4. This is 4.5. Like just right there. So if I connect all the dots. It's already blue. That's fine. So basically, I just go here, and then from here to here. Oops, let me just do that again. So from here to here, then from here to here, and then from here to here. Great, and as you can see, everything just basically, in the y direction, everything gets multiplied by 1.5, and the x's don't change at all. So in other words, the outputs are affected, but none of the inputs are affected because the x's don't move at all. All right, so let's move to number 2. Let me just extend the page a little bit. Just move up a bit. Here we go. All right, so oops. All right, so let's look at this one. So here we have, so I'll just write this as number 2. Y is equal to f of 2x. So let's look at the, again, R, S, T. We just always have to look at those 3 things because those are the order of transformations. So is there any reflection? No. Okay. Is there a stretch? Yes, but this time it's inside the argument. And remember, if it's inside the argument, it affects the inputs. And since this is a 2x, remember 2 we sort of called as sort of an efficiency factor if you remember in class. So in other words, all the x's actually, in order to get the same output, we just need half the amount of the input because 2 times half will basically give you the same sort of argument in order to get the same output. So the stretch here is we say there is a horizontal stretch. I'm going to write HS, horizontal stretch by half. Okay, which means that all the x's, instead of not 2x over here, but remember it's the reciprocal, so it's a horizontal stretch by half. And there's no translation here, so basically that's it. So what that means for all the x's is that all the x's get multiplied by half. The y's stay put because we don't have any vertical stretch, so the y's stay put. So since the y's stay the same, we can just literally list them down. -2, 4, 1, 3. And if we take half of these, this will be -1. Right? This will be -1. This will be -0.5. 0 times half is still 0. 2 times half is 1, and 3 times half is 1.5. So let's see how this looks like. So this one is -1, 2. So -1, 2. So that's this point right there. The next one is -0.5, -2. So -0.5, -2. So it's just right there. This one is 0.4, which basically is the same point right there. This one is 1, 1, so 1, 1, which is that point right there. And the last one is 1.53, so 1.53, which is that point right there. So if I connect the dots, basically if I connect the dots right here, I get something like that. I connect this with that one right there. And then I connect that one there, that one right there. And as you can observe, the blue W, it sort of gets compressed by a factor of 2, which basically means you get the same outputs. Remember, the Y's don't change. You get the same outputs for even smaller inputs. So in other words, because we have that 2 efficiency factor, everything gets compressed by 2, so all the X's are lesser than what they were before. So we get this sort of compressed W compared to the previous one. All right, so number 3. Let's do number 3. Y is equal to f 0.5x. So once again, R, S, T, right? There's no reflection as we can see, so there's no reflection. There's a stretch this time, but remember it's in the argument. So whenever the coefficient is within the argument, it affects the horizontal. And since this 0.5 is really, another way of writing it is f of 1/2 x. That's just another way of writing it. F of 1/2 x. So basically we say that there's a horizontal stretch by a factor of 2. So remember, we always take the reciprocal when it's inside the argument. And finally, when we look at the translation, we don't see any translation, so basically there's no translation. So the only transformation here is the stretch, horizontal stretch by 2. So let's see how that affects that. So what that means is all the x's get multiplied by 2. So 2x, the y's stay the same. So this becomes -4, 2. Oh, actually, let me just write the 2's first because since they don't change at all. -2, 4, 1, 3. And for the x's, since everything gets multiplied by 2, it's -2 times 2 is -4, -1 times 2 is -2, 0 times 2 is 0, 2 times 2 is 4, and 3 times 2 is 6, right? So these are a new set of coordinates. So let's just plot them. So this one, remember, everything basically gets stretched out by a factor of 2. So this is -4, 2 there, -2, sorry, this one is -2, -2, so -2, -2 becomes like that. 0, 4, so 0, 4 stays put, nothing, that does not change at all. So 0, 4 is right there. 4, 1, so 4, 1. That's that point right there. And finally 6, 3, so 6, 1, 2, 3. So that's that point right there. And if we just connect all the points, we get that one goes like this, and that one goes like that, like this, and finally like that. So as you can see, when we have 1/2 x, which means we now need twice as many inputs in order to get the same output. So all the x's get stretched out by a factor of 2. So since they all get stretched out, the w's or our graph basically widens in the horizontal direction. So that's basically the solution for that one. Let's move on to the next one. I just need a little bit more room. So let's move up here. So, oops. Okay, so let me write this as number 4. Okay, so here I have, actually so it's interesting, it's 2f of 2x. So let's look at all the reflections translation. Let's look at all the transformations. So once again, I don't see any negatives, so there's no reflection. Okay, so let's look at s. So the first thing that you can observe is the 2 outside, so the coefficient of f. So if we look at the coefficient of f right here, we can see that it's a vertical stretch by a factor of 2. So what this means is, let me start this. So it's a vertical stretch by 2. So in other words, this number here is dealing with the vertical stretch. Now let's look at the argument itself. So since this is f of 2x, remember we said that when the coefficient is inside the argument, this number can be seen as an efficiency factor. So in other words, we are basically compressing all the x's by a factor of 1/2. Remember, we're just doing the reciprocal of the coefficient inside the x. So another way of saying this, so we have a vertical stretch by 2. That means all the y's get multiplied by 2. And then all the x's, so it's a horizontal stretch by half. So inside the argument, it's by half. So now let's look at the last one. Let's look at the translations. There's no plus or minuses, so there's no translations. So that's that. So how does that affect the graph? So let's look at the vertical first. In other words, let's look at the y's. So all of them are multiplied by 2 because we just said that's a vertical stretch by 2. So this becomes 2y. And now this one is a horizontal stretch by half, so this is half x. Right? So now all we have to do is just take these x's, multiply them by half, and take all these y's and multiply them by 2. So let's do the y's first because that's a little bit easier. So 2 times 2 is 4, negative 2 times 2 is negative 4, 4 times 2 is 8, 1 times 2 is 2, 3 times 2 is 6. Okay, so we have that. Now let's do the x's. With the x's, it's half. So in other words, it's negative 1, negative 0.5. 0 times half is simply 0. 2 times half is 1. And 3 times half is 1.5. So all we have to do now is plot these set of points. So it's negative 1, 4. So negative 1, 4. So negative 1, 4 will be right there. Okay. Next one is negative half, negative 4. So negative half, and then negative 4 is right there. Just being as careful as I can. 0, 8. So 0, 2, 8. So 0, 8 is right there. Okay. 1, 2. So 1, 2 is right there. And 1.5, 6. 1.56. So there's 4 and there's 6. So let me just connect these dots. So I have that one there, which goes to here. And then I have this one here, which goes to there. And then I have this one here, which goes to about there. I have this one here, which goes to about there. So as we can see, what's happened is that in the x direction, it's being compressed. So that's why this w sort of looks compressed in the x direction, but in the y direction, it's being stretched by 2. So that's why it looks like a very stretched out in the y direction, but very compressed in the x direction. And it's because of these transformations. So it's very, very important to remember. I think the y's are easy to do, but the x's, you have to remember that you must take the reciprocal of whatever coefficient is in front of x. All right, so let's move on to the next one. All right, so let's move on to number 5 over here. So for number 5, which as we see right here, is y is equal to negative f of x. So let's look at the transformations again. So there's r, s, t. These are basic ones. Right? Remember, the order is very important when you're going from f of x to whatever. So anyways, we can see that the coefficient here is negative 1 outside the f, and it affects the output. So if it affects the output, all it means is it affects the y's. So, and since it affects the y's, basically all the y's will flip over. Not the x's, but all the y's. So in other words, what was a positive y will become a negative y, and what's a negative y will become a positive y. So in other words, it will flip over this axis right here. So this is the x-axis. So we can see this as a reflection. I'm just going to write REFL, but on the test you're going to write reflection. Reflection across the x-axis. X-axis right here. We don't see any stretches because there's no numbers, no coefficient in front of the f, or any coefficient in the argument for the x. So there's no stretch, and there's no plus or minus basically to add to the function, to add to f, or even in the argument, so there's no translations whatsoever. So in other words, since there's a reflection across the x-axis and it's only affecting the y's, affecting the output since there's a negative in front of the f, basically this will become negative y. Since the inputs stay the same, the x's just stay the same, so x just stays put like that, so there you go. So what we can see is that the x's stay put, so this becomes negative 2, negative 1, 0, 2, 3, and for the y's, we see this as negative 2, 2, negative 4, negative 1, and negative 3. all the y's just get multiplied by -1, so that's why they're this. That's why this is what you see over here. So now we just have to plot this. So it's -2, -2, so -2, -2 is here. -1, 2, -1, 2 is here, right? 0, 4, so 0, 0, -4, so 3, -4 is right here. 2, -1, 2, -1 is right here, and 3, -3 is right here. Okay, so let's basically do this right now. So all we have to do right now is just connect the dots. Oh, let me just use a different color. So let me just use blue. Use blue right there. So let's go from here to there, and then from there to this point right here, and then we have from here to there, and then from here to there. So as you can see in this sort of blue graph, all we've done is just reflect all the y's across the x-axis, which is why it ends up looking the way it does. All right, so now let's move on to the next one, which is, let's extend the page a little bit. So let's do this one. Oops. Okay. Okay, there we go. So let's do it. So this is number 6. So here we see y is equal to f of -x. So here we have y of f of -x. Again, once again, RST. So RST. So we can see in the reflection that none of the outputs are changing because there's no coefficient in front of the f. But we can see inside the argument that the x has a coefficient of -1. So we do see a reflection this time, which means that all the x's will flip across this axis. So since the x's will flip across this axis, this is the y-axis, so which means that there's a reflection, REFL, which stands for reflection, across the y-axis. Okay, so since there's a reflection across the y-axis, and that's basically it, there's no other reflection. There's no stretch, we don't see any numbers, any coefficients in front of the f or the x other than like -1, but we took that as the negative, we took that for the reflection. So there's no stretch, and again, there's no translations as we can see over here. So in this case, all the x's, since it's a reflection of the y-axis, don't be confused. Even though we say y-axis, it's really the x's that are being switched. So in other words, this becomes -x. The y's, there's no reflection, so basically the y's stay put. So let's just write the y's down first since they stay the same. So 4, 1, 3. And all the x's now get multiplied by negative. So this becomes 2, 1, because -2 times 1 is 2, -1 times -1 is +1, 0 times -1 is simply 0, 2 times -1 is -2, and finally 3 times -1 is -3. Okay, so let's just do this. So 2, 2, so 2, 2 would be here. Okay, 1, -2, 1, -2 would be here. Okay. 0, 4, 0, 4 is basically where it is, so right over there. -2, 1, so -2, 1 would be right there, and -3, 3, so -3, 1, 2, 3 would be right there. So let's just connect the dots now. So, oops, if we connect this dot with the one right there. Okay, and then this dot with the one right there. This dot with the one right there. And then this dot with the one right there. And what you can see is that the graph has the outputs stay the same. The outputs stay exactly the same, but it's just the inputs have been flipped across the y-axis. So we get this sort of reverse-looking W compared to the original one. So that's basically the transformations right there. Okay, I think we just have a few more. Oh, we have a few more pages. Okay, so 2, 4, 6, 8. So I think we have 8 more questions here. So let's carry on. So that was 6. This will be number 7. Okay, so now we have y is equal to f of x plus 3. So again, same deal as before. So r, any reflections? I don't see any negatives in front of the f or inside the argument. So in other words, there's no reflection. Is there any stretch? I don't see any numbers in front of the f or inside the argument, so there's no stretch. Is there a translation? Yes, because we see it's a plus 3, which will affect the outputs. So in other words, basically we have a vertical translation. So we have a vertical translation. So VT stands for vertical translation. And since it's plus 3, it's going to be up by 3 units. Okay, so it's a vertical translation up by 3 units. So what does that mean? So since the inputs don't change, see the x over here, there's nothing being added within the function. It's only in the outside of the function, in other words, affecting the outputs. So x actually stays put. Okay, it's really the y's that are being added by 3. So all the y's being added by 3. So in other words, x stays put. So this is -2, -1, 0, 2, 3. And the y's are being added by 3. So this becomes 5, because 2 plus 3 is 5. -2 plus 3 is 1. 4 plus 3 is 7. 1 plus 3 is 4. And 3 plus 3 is 6. Okay, so now we just have to plot these. So -2, -2, 5. 1, 2, 3, 4, 5. -1, 1. -1, 1 is right there. 0, 7. So this is 0, 1, 2, 3. So it's right there. Okay. 2, 4. So 2, 1, 2, 3. So that's 4 right there. And 3, 6. So 3, 1, 2, 3, 4, 5, 6. So it's right there. And now all I'm going to do is just basically connect the dots. So I have this being connected right to there. This being connected to there. That's being connected to there. And oops, it's not right. That's being connected to there, and that's being connected to right there. So all you can see is that this graph has just basically been pushed up by 3 units, which makes sense because f of x plus 3, and since it's a vertical translation, up by 3 units. That's all it's done. It's just move it up by 3. And also remember one thing, which is the way to write this translation is if we write it in vector form, this would be 0 because it hasn't been moved left or right. Remember, the first part of the vector form tells you if it moves left or right, which is it hasn't, but it's been moved up by 3. Okay, so this is how you would write this translation in vector form. Let's move it up to the next one. So, okay, so now basically we see y is equal to f of x before. So in other words, none of the outputs are changed because there's no plus outside of the f. It's all within the argument. So anyways, let's just look at RST. So reflection, there's no reflection. I don't see any negatives anywhere, so there's no reflection. Is there any stretch? I don't see any stretch. There's no numbers in front of f and no number in front of the coefficient of x. So in other words, there's no translation here, no stretch here. But let's look at the translation. We see it's x plus 4. And if you recall, what this means is that this is not to the right 4, but it's to the left 4. Whenever it's plus, x plus 4, it means to the left. And if it was minus, it would mean to the right. So basically, it's a horizontal translation. So it's HT. That's for horizontal translation. Let me just say, oh, it's HT. HT, 4 units. And we're going to say left. Very important to say that. 4 units left. And basically, the way to write this in vector form, since it's 4 units left, is -4. And since there's no vertical translation, we would just say 0. So this is how to write this in a vector form, where all we're doing is moving 4 units left, and we're not moving up at all. So since we're moving 4 units left, this would be x minus 4, and the y stays put, since there's no vertical translation. So let's just write all the y's, -2, 4, 1, 3, and all of these would be subtracted by 4. So -2 minus 4 is -6. -1 minus 4 is -5. 0 minus 4 is -4. 2 minus 4 is negative 2, and 3 minus 4 is negative 1. So let's just plot these. So we have 2, 4, negative 6, 2, which is right there. Negative 5, 2, negative 5, negative 2, which is right here. Negative 4, 4, so negative 4, 4, so that's right there. Negative 2, 1, negative 2, 1 is right there. And finally, negative 1, 3, negative 1, 3 is right there. So let's just connect these dots and see what that looks like. So we get that. We get that there. We get that there. And we get that there. So all we can see is that basically it's just been moved to the left. It's just moved to the left, and that's clear over here. And none of the y's change. None of the y's change at all. It's only the x's that have been moved to the left. I believe this is number 8. Number 8. Okay, so that's number 8. Okay, let's move to the next one. All right, so here's something a little bit more interesting. So now we have some reflections, we have some transformations and stretches, so let's just go over it again. Okay, so again, RST. So let's look at R. So we can see that the coefficient in front of the F is negative 2. And really, we're not concerned about the 2, but we're more concerned about the negative. And since there's a reflection in the y coordinates, basically all the y's will flip, it's basically a reflection across this way, right? So since all the y's will flip, it's a reflection across the x-axis. So it's a reflection across the x-axis. Okay, so that's our reflection. Remember, the negatives only sort of deal with the reflection. Let's look at the stretches. The stretches, we don't see anything in the argument. So if you look in the argument, we see a -3, but that doesn't have that's not the coefficient of x. So that has something to do with the translations, and we'll get to that in a second. But if you look at x right here, there's no coefficient, there's no number in front of x. So there's no reflection, or basically or any stretch with the x coordinates. But if we look outside with the f, we see a 2. Now remember, we're not considering the negative anymore because we've taken care of that. That deals with the reflection. The 2 basically says that there's a vertical stretch. There's a vertical stretch by 2. In other words, all the y's get multiplied by 2. And there's no horizontal stretch, so we don't even have to write that. Now let's look at the translations. So if we look at the translations, let's look at the x's first. So we see x minus 3. And remember that when there's a translation in the argument, if we see minus, it really means to the right. So in other words, so I'm just going to write right by 3 units, okay? And then we see a -1 over here, which means that it's down by 1 unit. So down by 1 unit. Right? And what that means is if it's right, this is a horizontal translation 3 units to the right, and down by 1 unit is a vertical translation 1 down. So let's just figure out how this will all work. So let's look at this one first. A reflection across the x-axis, right? So that deals with the y's. So basically, we'll have a negative over here. We see a vertical stretch by 2. So in other words, it's negative 2y. Okay. So because the vertical stretch only affects the y's. And let's look at the vertical translations. It's down by 1 unit. So it's negative 2y. So we do those two first, and then we translate it down. So we subtract 1. Okay, so that's how this will affect it. Now let's look at the x's. There's no reflection in the x's, so we don't have to worry about that. There's no stretch by this, so we don't have to worry about that. So basically, it'll still be x. Right? We don't have to put any negative. We don't have to put any number in front because there's no reflection or stretch. Let me just get rid of that. And then, however, there is a translation which says it's moved to the right 3 units. So it's going to be x plus 3. Okay. So since we have this, let's just see how this works. So x plus 3, so in other words, negative 2 plus 3, so that's going to be 1. Negative 1 plus 3, that's going to be 2. This is going to be 3. 2 plus 3 is 5. and 3 plus 3 is 6. So this 3 plus that 3 is equal to 6. Now let's deal with the y's. So what this means is you just take these y's and then plug it into here. So this 2 times negative 2 will be negative 4, and negative 4 minus 1 is negative 5. Negative 2 times negative 2 is positive 4. 4 minus 1 is 3. 4 times negative 2 is negative 8. Negative 8 minus 1 is negative 9. 1 times negative 2 is negative 1. Negative 1 minus 1 is, negative 1 times negative 2 is negative 2. Negative 2 minus 1 is negative 3. And 3 times negative 2 is negative 6 minus 1 is negative 7. So now these are a set of coordinates that we have to plot. Okay, so it's 1, negative 5. So 1, 2, 3, 4, 5. Okay, next one is 2, 3. So we have 2, 1, 2, 3. We have that right there. 3, negative 9. So 3, negative 9. So I don't know even if I have enough spots, but okay, let's just see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh wow, just made it. So negative 9. 5, negative 3. So 1, 2, 3, 4, 5. 1, 2, 3. Okay, and finally 6, negative 7. So 6, 3, 4, 5, 6, negative 7. Right there. Okay, so let me just connect these dots and see what that looks like. So we have this, goes from there to there. This, that goes from there to there. There. And let's just see if that sort of makes sense, because first we have a reflection across the x-axis. So basically it's being flipped across and it sort of looks like that, yes. Then all the y's are being stretched, so yeah, it looks stretched in the y. And then it's being moved 3 to the right, so yeah, it looks like it's moved 3 to the right, and then down 1. So that's sort of like, just from, based on the RST, we can see that it sort of looks right. And yeah, and this is basically how you do it, and once you plot those points, you should basically get the same graph. Okay, let's look at the next one. I believe that was number 9, and so this will be number 10. Let me just do this here. Number 10. Okay, so here we have, now observe that in the argument it's factored. Okay, it's already factored, so we don't really have to worry about factoring it, but later on we might have to. So let's look at RST over here. So R, if we observe over here, the coefficient in front of this x plus 1 term over here is negative 0.5. So what this means is that all the x's, all the inputs will be reflected. So if they're reflected, they will be reflected this way. So across the y-axis. I'm just going to erase this, just because that might affect it later. But I'm going to reflect. So in other words, it's a reflection. It's a reflection across the y-axis. Okay? So we got the r's. And there's no other negatives outside, so basically it's just only with the y. So dealing with the x's. Let's look at s. So the stretches. So we look at the stretch. We see that there is no vertical stretch because there's nothing in front of the f, but there is a horizontal stretch. So keep in mind that 0.5 is half. And remember, we treated that as an efficiency factor. So in other words, this is half as efficient. So if it's half as efficient, we need twice as many x's to basically get the same output. So in other words, this is a horizontal stretch by, so remember, half is 1 over 2, and we need to take the reciprocal of that, so it's a horizontal stretch by 2. Is there any vertical stretch? No, because I don't see anything in front of the f. So this is, since there's no vertical stretch, that's the only stretch that we, the horizontal stretch. And finally, if we look at the translation, since it's already factored, we can see that it's 1 unit to the left. Remember, this is plus 1. So inside the argument, if we say plus 1, it means it's to the left. So basically, left 1 unit. Okay? And if we look outside of the f, we see there's a plus 2. So it's basically up 2 units. Okay? So that's RST. So now let's translate that. So we see that we said that there was a reflection across the y-axis, which means all the x's get changed, right? So right away we know that the x's will be negative. There's a horizontal stretch by 2, and that affects the x's only. So it's going to be negative 2x, okay? And it's going to be left by 1 unit. We know that this is a horizontal translation, so it's going to be minus 1. Let's look at the y's. There's a reflection across the y-axis, but not across the x. So in other words, the y's are not reflected whatsoever, okay? Is there any stretch in the y's? No, I don't see any vertical stretch. So basically the y's stay put. And let's look up the translations. It's up 2 units, so it's going to be plus 2. Okay, so since all we have to do now is just go from here to there. So negative 2 times negative 2 is positive 4, and 4 minus 1 is 3. Negative 1 times negative 2 is 2. 2 minus 1 is 1. 0 times negative 2 is 0. 0 minus 1 is negative 1. 2 times negative 2 is negative 4, minus 1, which is negative 5. And finally, 3 times negative 2 is negative 6. Negative 6 minus 1 is negative 7. Okay, let's do the y's. The y's are all being added by 2. So 2 plus 2 is 4. Negative 2 plus 2 is 0. 4 plus 2 is 6. 1 plus 2 is 3. And 3 plus 2 is 5. Okay, so 3, 4. All we have to do now is plot this. So 1, 2, 3, 1, 2, 3, 4. So that's 1 point. 1, 0 is 1, 0. So it's right there. 1, 0. Negative 1, 6. Oops. I don't know why that happened. So negative 1, 6, 2. Oh, sorry. It's negative 1, positive 6. So negative 1, 2, 4, 6. Okay. Negative 5, 3. So 1, 2, 3, 4, 5. Negative 5, and then 1, 2, 3 is going to be right there. And finally, negative 7, 5. So negative 7, and then 3, 4, 5 is right there. Okay, so now all we have to do is just connect the dots. So I'm just going to go backwards. So we have right there. That connects to right there. That connects to right there. And then that connects to right there. And there we go. And this sort of makes sense. It's a reflection across the the y-axis. So all the x's get flipped, as we can see. And then it gets moved 1 to the left. So it sort of looks like it's to the left. And then up 2. So, oh, and then don't forget the stretch. Although all the x's also get stretched by 2. So it looks a little bit stretched out. So this sort of looks right. So we kind of know that we're on the right path. All right. Always do a visual confirmation. Always do a visual confirmation. It really helps. So I think we're almost near the end. We just have like 4 more problems and then we're done. So let's do number 11. So here, okay, so if you look at the argument is not factored. So the first thing before you even write RST is you must factor it. So it's 2f of, and you're going to factor out the number or the coefficient in front of the x. So we're going to factor out negative 0.5. And then so what we're going to put in brackets is x. Now, negative 0.5 times what will give you positive 2? And that is actually going to be negative 4. Okay, because negative 0.5 times negative 4 is positive 2. So then we're going to close the bracket there and we have the minus 2. Okay, so it's factored. It's extremely important that you factor first before you start doing any of the transformations. Now let's just look at RST. I'll just use a different color, just RST. Okay, so if we look at R, there is a reflection, but again, this is in the over the y-axis because it's only going to affect the x's, so it's going to be this way. So there's a reflection across the y-axis, okay, which means that it's only going to affect the x's, okay, and so that's the negative over there. Now let's look at the stretches. We see that there's a vertical stretch by a factor of 2, so it's a VS by 2. Okay. Now, the other number that we see here is 0.5. Now, don't worry about the negative because we took care of that with the reflection over there. So we don't have to deal with that negative anymore. We just have to deal with the 0.5. Now remember, the 0.5 is inside the argument. Since it's inside the argument, what this means is our efficiency factor, so it's half as efficient. So that means we need twice as many x's in order to get the same output. So if we need twice as many x's, so what this means, it's a horizontal stretch by 2. Remember, this is 1 over 2, and since when we're doing the stretch for the horizontal, we're going to take the reciprocal. So the reciprocal of 1 over 2 is 2, so therefore we have a horizontal stretch by 2. This 2 over here, it comes from the vertical stretch right there. These two are not related, okay? They are completely separate. So this 2 is separate from that 2. Okay, and finally translation, we can see x minus 4. Since we see an x minus 4, we know that's to the right because it's inside the argument. So basically it's right. I'm just writing right, but you should really write horizontal translation to the right by 4 units. So right by 4 units. Okay, and this is negative 2, so it's down by 2 units. So down 2 units. Okay, so how does that translate into this table? So it's a reflection across the y-axis, which means that it affects the x's only. So we know right away that it'll start with a negative. There's a horizontal stretch by 2, so which means it's negative 2x. So all the x's get multiplied by negative 2. Okay, and it's to the right by 4 units, so it's plus 4. Okay, so now let's do with the y's. The y, there's no reflection, so there's no negative with the y's. There's a vertical stretch by 2, which means all the y's get multiplied by 2, and it's down by 2 units, so it's minus 2. So all we have to do is take these x and y's and plug them into this, and we get our new set of coordinates. So negative 2 times negative 2 is positive 4. 4 plus 4 is 8. Okay. Negative 1 times negative 2 is positive 2. 2 plus 4 is 6. 0 plus 4 is 4. 2 times negative 2 is 2 times is negative 4. Negative 4 plus 4 is 0. And 3 times negative 2 is negative 6. And negative 6 plus 4 is negative 2. Okay, so we got that. Now, with the y's, let's do that. So 2 times 2 is 4. 4 minus 2 is 2. Negative 2 times 2 is negative 4. Negative 4 minus 2 is negative 6. 4 times 2 is 8. 8 minus 2 is 6. 1 times 2 is 2. 2 minus 2 is 0. And finally, 3 times 2 is 6. And 6 minus 2 is 4. Right? So these are a new set of points, and now all we have to do is just plot them. So we have 8, 2, so 2, 4, 6, 8, and 1, 2. So we have that point over there. 6, negative 6, so 2, 4, 6, 1, 2, 6. Let me just get that right. 3, 4, 5, 6. Yeah, okay, so 6, negative 6, and then 4, 6, so 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6. Okay, 0, 0, which is right here, and then negative 2, 4, so 1, 2, 3, 4, right there. All right, so let's connect these dots. So if we connect these dots, we go something like that, and then we go from there to there, and then we go from there to there, and we go from there to there. And let's just see if that sort of visually makes sense. First, there's a reflection. So yeah, it does look like there's it's flipped over the y-axis. Then this vertical stretch by 2, yeah, all the y's look stretched by 2. Horizontal stretch by 2, yeah, all the x's look a little bit stretched out. Then it's to the right, yeah, it looks like it's moved to the right. And down 2, yeah, it sort of looks, it doesn't really look like it's down 2, but remember, we stretched it, so it already increased it, and now we've moved it a little bit further down. So had we not, this would have been even further up. Okay, so that's number 11. I think we have 3 more to go. Let's just move to the next one. Do that. Okay, number 12. All right, so again, this is not factored. The argument is not factored, so we have to factor that out. So it's negative 1.5 f, and we're going to factor out the 2, so it's 2 x plus 3, okay, minus 2. Okay, so let's look at RST. So so the reflection is, we see a reflection. Now, it's not in the argument. We don't see a negative in front of the coefficient here, but we see a negative in front here. So it's a reflection for the y's. So if all the y's are being flipped, they would flip across the x-axis. So it's a reflection across the x-axis. Okay, so we've got a reflection across. There's no other reflection, so we don't have to worry about that. S. Now we see the 1.5. Now we don't have to worry about the negative anymore because we took care of that in the reflection. So all the y's are going to be multiplied by 1.5. It's only going to affect the output. So basically it's a vertical stretch by 1.5. Okay. Now if we look at the x's, we see a 2 over here. And remember, this is an efficiency factor. So if this is 2, that means we just need half as many x's to get the same output. So in this case, this is going to be by 1/2. Okay? And finally, for the translation, we can see that this is x plus 3. So remember, whenever it's plus inside the argument, it just means to the left. So left 3 units. Left 3 units. And it's down 2 units. So down 2 units. Okay? So let's look at how that sort of changes this. So it's a reflection across the x-axis. So if it's a reflection across the x-axis, none of the x's change. None of the x's change, right? There's no negative inside here, so none of the x's change. However, there's a horizontal stretch by half, so all the x's get multiplied by half, right? And it's to the left 3, so they get subtracted 3. Now let's deal with the y's. We can see that there's a reflection across the x-axis, which means all the y's will change. So we know that it's going to start off with a negative. It's a vertical stretch by 1.5, so it means all the y's get stretched by 1.5y. And it's down 2 units, so it's minus 2. Okay? So now all we have to do is take these x's and y's and put them into this and figure out what's going to happen. So negative 2 times half is negative 1. Negative 1 minus 3 is negative 4. Negative 1 times half is negative 0.5, so it's negative 3.5. Negative 0 times half, so this is going to be negative 3. 2 times half is 1, so 1 minus 3 is negative 2. And 3 times half is 1.5, so 1.5 minus 3 is negative 1.5. All right, let's do this. So the y's get multiplied by negative 1.5. So 2 times negative 1.5 is negative 3. Negative 3 minus 2 is negative 5. Negative 2 times negative 1.5 is 3. 3, that's positive 3. 3 minus 2 is 1. 4 times negative 1.5 is negative 6. Negative 6 minus 2 is negative 8. 1 times negative 1.5 is negative 1.5, so that's negative 3.5. And finally, 3 times negative 1.5 is negative 4.5. Negative 4.5 minus 2 is negative 6.5. So 3 times negative 4.5 minus 2, yes. No, sorry, minus 5.5. Let me just change that. Oh wait, let me just change that again. So 3 times negative, yeah, sorry, it's negative 6.5. I was right the first time. Right, so 3 times negative 1.5 is negative 4.5. Negative 4.5 minus 2 is negative 6.5. Now all we have to do is just plot these. All right, so negative 4 minus 5. So 1, 2, 3, 4. 1, 2, 3, 4, 5. So that's our first point right there. Second one is negative 3.51. So negative 3.5 1, so it's right there. Negative 3, 8, negative 3, negative 8, so negative 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Negative 2, negative 3.5, negative 2, negative 3.5, and negative 1.5, negative 6.5. So negative 1.5, 4, 5, 6, negative 6.5 would be somewhere right there. Okay, so now we just have to connect the dots. All right, so there, and we go there, and then we're going there, then we go there. And let's just see if it visually makes sense. There's a reflection across the y, so yeah, it does look reflected. It's stretched by 1.5 in the y direction, so yeah, it looks a little bit stretched. It's stretched by half, so in other words, it's being compressed, really, and it does look a little bit compressed. Left 3 units, yeah, it looks a little bit to the left. Down 2 units, yeah, it looks a little bit down. So from a visual standpoint, it looks right. Let's move on to the last two. Okay, so this one, I forget what number it is. I think that was number 13 or something. So again, this is not factored because we don't have the x as a positive. So this is negative 2 f of, what you're going to factor out is always the number in front of the x. So it's negative 1, and then it's going to be x minus 5. So negative 1 times x is negative x, and negative 1 times negative 5 is positive 5 plus 3. Okay? So this is the factored form. So once you get a factored form, then you can do RST. So the reflection is across the y, so it's a reflection across, the reflection is for all the y coordinates, so since it's a reflection for all the y coordinates, it's a reflection across the x-axis. So it's a reflection across the x-axis, and since we see a negative over here, it's also a reflection since all the x's will be flipped, so it's a reflection for all the x's, so it's also a reflection across the y-axis. So it's a reflection across the x and the y-axis, which means both the x's and y's will become negatives of what they were previously. Now let's look at the stretch. So if we look at the vertical stretch, we see it's 2. We don't have to worry about the negative once again because that's taken care of in the reflection. So this is going to be a vertical stretch by 2. Okay. Now let's look at the horizontal. This is simply 1, and we don't have to worry about the negative because that was taken care of in the reflection. So if we look, since this is 1, we don't even have to write, but we can. It's a reciprocal of 1. The reciprocal of 1 is basically 1, so it's a horizontal stretch by 1. I didn't actually even have to write that, but I just wrote that for the sake of it because it won't affect it. X times 1 is simply x, so it won't affect it at all. And since this is x minus 5, which means all the x's will move to the right, because remember it's in the argument, so it's minus within the argument, it's to the right. So it's right by 5 units, right by 5 units, and it's up by 3 units, up 3 units. Okay, so how does that look like on this part? Okay, so we know that there's a reflection. Let's deal with the x's first. So there's a reflection in the y-axis. Since there's a reflection in the y-axis, that means all the x's will be affected. So it's negative. We know that there's a stretch by 1, so basically we can say it's negative 1x. Okay, we didn't even have to write the 1, but I just did that anyways. And it's to the right by 5 units, so it's going to be plus 5. Okay. For the y's, there's a reflection across the x-axis. It's being reflected this way. So it's going to be negative for sure. It's a vertical stretch by 2, so it's negative 2y. Okay, because it's negative times 2, so it's negative 2y. And it's up by 3 units, so it's going to be plus 3. So right affects the x's, and up and down affects the y's. Now all we have to just translate, just get these new set of coordinates and then plot them. So this is going to be negative 2 times negative 1, which is positive 2. 2 plus 5 is 7. This one will be 1 plus 5, so that's 6. This will be 5. 2 times negative 1 is negative 2. Negative 2 plus 5 is 3. 3 times negative 3 is negative 3, or times negative 1 is negative 3. Negative 3 plus 5 is 2. Let's do the y's. Negative 2 times 2 is negative 4. Negative 4 plus 3 is negative 1. Negative 2 times negative 2 is 4. 4 plus 3 is 7. Okay. 4 times negative 2 is negative 8. Negative 8 plus 3 is negative 5. 1 times negative 2 is negative 2. Negative 2 plus 3 is simply 1. And finally, 3 times negative 2 is negative 6. Negative 6 plus 3 is negative 3. Let me just check this one more time. This is negative 4 plus 3 is negative 1. 4 plus 3 is 7. Negative 8 plus 2 is negative 5. Negative 2 plus 3 is 1. And negative 6 plus 3 is negative 2. Okay, great. So this is correct. I'm just going to erase these sort of reflections just because I need to make room for the points themselves. Okay, so 7, 1. So 2, 4, 6, 7, 1. So we have that 1 point there. 6, 7. So 6, 1. So 2, 4, 6, 7 right there. 5, negative 5. So 2, 4, 5. So 2, 4, 5. So 5, negative 5 is right there. 3, 1. 3, 1 is here. Okay, and 2, negative 3. 2, 1, 2, 3 is right there. Okay, so let's just connect the points. So we have that there, that there, that there, and that there. And let's just see if it makes sense. We have a reflection across the x-axis, which would make it look like that, and then y-axis, yeah, so this sort of looks like it's being reflected both ways. Vertical stretch by 2, so all the y's look stretched by 2. Horizontal stretch by 1, there's no real horizontal stretch. Right 5, yeah, that makes sense, and up 3. It doesn't really look up per se, but remember we did some reflections, which is why it sort of ends up looking like this. So had we not done the reflections, it would probably have looked further up, but anyways, that's basically sort of like a visual sort of confirmation of our points right there. Okay, now this is the very last one. The very last one, so let's just do this. So I think this is number 14. Okay, so let's do this one. So remember, the argument is not factored, so we must factor it first. So this is negative 0.5. That's distinct. Okay, so we have to factor out the number, the coefficient in front of the x, which is negative 0.5. So it's negative 0.5. And it's negative 0.5 times what will give you positive 2. So negative 0.5 times negative 2, or negative 4, sorry, will give you positive 2. So negative 0.5 times negative 4 is positive 2 right there, plus 3. Okay, so let's look at RST again. So R is simply, there's a reflection across the, so this means that all the y's will flip. So it's a reflection across the x-axis. And this negative here means that all the x's will flip. So there's a reflection across the x and y. So reflection across, across x and y axis. Okay, so we got the reflection. Now let's do the stretches. So we can see that for the y's, they'll be multiplied by half. We don't have to worry about the negative because that was taken care of in the reflection. So it's a vertical stretch by half. It's a vertical stretch by half simply because of that. Now in the x direction, or the horizontal stretch, remember this is considered as an efficiency factor. So since this is 0.5, this is half as efficient. So in other words, we need twice as many x's to get the same output. So in other words, this is a horizontal stretch by 2, because 2 is the reciprocal of 1/2. And the translations, as we can see, is it's 4 units to the right. Remember, within the argument x minus 4, the minus 4 here means it's 4 to the right. 4 right. And with the vertical, it's 3 up. Okay, so let's see how this translates, or into this equation. So reflection across the x and y axis, so that means the x's, there will be negative. It's a horizontal stretch by 2, so it's negative 2x, okay? And it's 4 to the right, so it's plus 4. Let's do the y's now. There's a reflection across the x-axis, which means it affects the y's, so it's negative over there right away. It's a vertical stretch by half, so it's negative half y, okay? And it's up by 3, so it's plus 3. Okay, so now let's just see how this works. So negative 2 times negative 2 is positive 4. 4 plus 4 is 8. This is going to be 2 plus 4, which is 6. This is going to be 4. 2 times negative 2 is 4. 4 plus 4 is 0. 3 times negative 2 is negative 6. Negative 6 plus 4 is negative 2. Okay, great. So now let's do the y's. So 2 times negative half is negative 1. Negative 1 plus 3 is 2. Negative 2 times negative half is positive 1. 1 plus 3 is 4. 4 times negative half is negative 2. Negative 2 plus 3 is 1. 1 times negative half is negative half. Negative half plus 3 is 2.5. And finally, 3 times negative half is a negative 1.5. Negative 1.5 plus 3 is simply 1.5. Let me just see if everything's correct. Yeah, okay, everything does seem right. Yes, everything does seem right. Okay, all right, so now let's just plot this. So I'm just going to erase this. Okay, so we got 8, 2, so 2, 4, 6, 8. And 8, 2 is right there. Okay, so that's our 4 points. 6, 4. So 2, 4, 6. 1, 2, 3, 4. Okay. 4, 1. 4, 1. 0, 2.5. So 0, 2.5 is right there. Okay. And negative 2, 1.5. So negative 2, 1.5. is right there. Okay, so let's just connect these points. So we have that right there. We have that right there. We have that right there. Have that right there. Okay, so let's just see if it visually makes sense. All the y's, first of all, have been reflected. So we have a reflection this way and a reflection that way. So you can sort of see that it would look like this and then like that. Yeah, try to imagine how the reflections would look like, and they would kind of look like this. Now, all the y's have been multiplied by half, so we can see that all the y's have been sort of compressed. All the x's have been stretched by a factor of 2, so you can see that it has widened, so that makes sense. It's moved 3 to the right, so yeah, 4 to the right, it looks 4 to the right, and then 3 up, it kind of looks, remember, it's been compressed too, so that's why it doesn't look as high up as it should be, but it was compressed first and then moved up, so that's why this is correct, and so it ends up looking like this, and that's the end of the exercise. So remember, always make sure that you factor first, then you write RST, then you get the set of points, and then you can always draw it out fairly easily. All right, so I'll see you in class next time, and hopefully we can do more transformations.